On Monday afternoon, 29th of October 1956, the Delta Wing supersonic B-58 moved for the first time under its own power. This occurred in a preliminary taxi maneuver which tested the braking characteristics, turning radius, and general overall ground hauling characteristics of the B-58. To this date, the airplane had undergone an Air Force Safety Board inspection, ground vibration checks, engine runs to full military power, and numerous other checkouts, all of which proved its readiness for the taxi test phase of operation. The Convair flight crew for this No. 1 B-58 is pilot B.A. Erickson, flight observer J.D. McEachern, and observer C.L. Harrison. Erickson, who had flew the first B-36 and YB-60, is the manager of the flight department at Convair's Fort Worth division. At approximately 16:30 hours, the B-58, with the flight crew on board, was pushed out of the engine run station No. 2 and towed to the starting position for the first taxi maneuver. Taxi screens were attached to the jets during this test to protect them against foreign object damage. The starting point for this test was the east-west taxi strip at the north end of the runway. The airplane was joined by the ground support equipment and fire trucks. Closed, and at approximately 1700 hours, engines were started. And as darkness closes in, the B-58 moves onto the runway and underwent its first taxi maneuver. This test proved that the B-58 ground handling characteristics were excellent, and the plane was given the green light to proceed with taxi runs. 1 week later, on the 5th of November 1956, the B-58 moved out of engine run station No. 2 under its own power and made its second taxi run. This was a low-speed run made from the north to south at approximately 40 knots. Excessive brake temperature, which developed in the aft inboard duals of the left main gear during the return taxi, caused a tire to blow after the airplane had come to a stop on the taxi strip. As soon as the wheel had cooled, ground crews came in to remove the tire and determine the cause of failure. Examination revealed that excessive temperature in the wheel was caused by a brake which didn't fully release. The tire change was completed in approximately 20 minutes, and the airplane was towed to the development hangar for building correction of the brake system discrepancy. The first high-speed taxi was made on Wednesday morning, the 7th of November, 1956. This run was made at a top speed of approximately 92 knots. The nose of the airplane was lifted to takeoff altitude for a very short time. Then, power was cut off and the drag chute deployed. There were no major discrepancies reported on this run. The second high-speed taxi was made after dark on the 8th of November 1956. The entire weight of the aircraft was lifted from the landing gear on this run, which was made at 138 knots. The only discrepancy encountered was a minor leak in the hydraulic system of the power control linkage package. On Sunday afternoon, 11th November 1956, while America celebrated Veterans Day, the B-58 taxied to the takeoff position for its first flight. Ground testing was now complete. Specifications had been met, and the B-58 was ready for its first flight. The weather for this occasion was perfect. The skies were clear, the air was mild, and there was a slight breeze from the south. Chase aircraft for this flight consisted of the Convair F-102A, which was used for observation purposes, and an F-94C, which carried the aerial cameras. At approximately 14:39 hours, the chase planes released their brakes, cut in their afterburners, and took to the air. After holding just long enough for the chase planes to move into position, the B-58 released its brakes and began a takeoff roll. Afterburners were not used. The B-58 was airborne at exactly 14:41 hours after a ground roll of approximately 3,300 feet. Airspeed at takeoff was 160 knots. The takeoff was routine and the climb was studied. Special flight data from the B-58 was telemetered back to a ground recording system in the flight test department. This information was monitored throughout the flight and recorded for future study. Information obtained here is supplemented by other flight data recorded on board. The airplane's future flights will be covered in a similar manner. After takeoff, the B-58, with landing gear extended, climbed to an altitude of 10,000 feet. The high landing gear is necessary so that the long fuselage can develop the ground angle required for takeoff and landing. Gear was retracted while the airplane was still at the 10,000-foot level. Operation was quick and smooth. Flight was then made to 20,000 feet, where the airplane was felt out at a speed of 0.7 Mach. At 15:19 hours, exactly 38 minutes after the takeoff, the B-58 settled on the runway to successfully complete its first flight. The drag chute was deployed immediately upon touchdown, and the airplane was brought to a short stop with a minimum amount of brake. The B-58 had come through its first flight with ease. Performance of engines and airplane had been routine. The B-58 supersonic bomber nosed into the engine run station at approximately 15:24 hours to conclude its first airborne excursion. The mechanical reactions of this airplane to its maiden flight are recorded on tape, but the reaction of the human element to the B-58 will be found on the faces of the crew. Of course, this is only the beginning. There will be many hours of grueling flight tests for the B-58 before it can properly be appraised as a weapon for the U.S. Air Force. But based on the first flight, it is reasonable to predict that the Convair supersonic B-58 will write a new chapter in America's Masters of the Sky.
Swift, capable, versatile, operational. Morning on a SAC flight line. An ordinary day. B-58 bombers perched in an alert posture await the day's activities. An ordinary day. But what of the extraordinary day when the strength and swiftness of that striking arm is put to the ultimate test? The B-58 weapon system has passed through its share of extraordinary days. Days when its performance pushed over the historical markers of manned flight. 18 September 1959, Carswell Air Force Base, Texas. On this date, the B-58 proved its low-level assault capability and, in the process, racked up an unprecedented flight accomplishment. Flying at speeds on the edge of sound, the Hustler was never more than 500 feet above the terrain in its race across 4 states, from Texas to California. In strategic terms, what did the flight add up to? First, it verified prediction that high-speed, low-level strikes are feasible and without a sacrifice in B-58 high-altitude supersonic operations. In fact, just 1 week later, this same aircraft reaffirmed its high-altitude capability by racing from Seattle to Waco at an average speed of 20 miles a minute. Next, the on-the-deck flight to California meant that the enemy is vulnerable to one more mode of attack. By hugging the valleys and skimming mountaintops, the B-58 can sneak undetected beneath enemy radar nets and avoid missile installations, making line-of-sight retaliation extremely difficult. Unique low-level, high-speed capability, penetration at small risk, pulverizing striking power, maximum chance of survival. These are the sum of what the B-58 accomplished in a few hours, 18 September 1959. 22 November 1960, Holloman Test Range, New Mexico. The mission? To make a fully automatic weapon release at Mach 2, twice the speed of sound, from an altitude of 50,000 feet. The mission, climaxing a series of test drops, was successfully accomplished this day by a B-58 Hustler. Pod separation was clean. The drop away of the free-fall bomb followed the calculated path. To the crew, all was routine. But it was one of the missions which gave Colonel James K. Johnson, commander of the 1st B-58 Wing, reason to say, we ought to get the best targets because we have the best airplane. 13 and 14 September 1960, Bergstrom Air Force Base, Texas. The 13th marked the opening of the 1960 SAC combat competition. On its debut, the B-58 Hustler won for its 43rd Bomb Wing crew the high and low-level bombing award. The first bomber to win such an award so soon after becoming a part of SAC's inventory. With only 40 days of preparation, a lone B-58 and 2 crews competed against 24 other crack crews flying 12 other bombers which had many thousands of operational hours under their wing. The quick reaction capability of SAC's new weapon system was vividly displayed by the B-58 crew. They approached the plane, boarded, started engines, and got wheels rolling in 2 minutes, 10 seconds, half the time required for SAC's other operational bombers. And crews scored 200 out of a possible 200 points for this event. Using only one combat-ready B-58 for both missions, its 2 crews scored 1,046 points, 137 points behind the first-place winner. Accuracy on both radar bombing runs was much better than aircraft specification requirements. Crews scored 198 out of a possible 200 points in aerial refueling, on each occasion taking on 40,000 pounds in less than 8 minutes. The importance of this refueling capability using existing tankers is clearly apparent. It means that the Hustler is intercontinental in range, can strike SAC targets the world over from bases within the United States. Indeed, the performance of the B-58 constituted an overall demonstration under combat conditions of SAC's present mission capability. Although not competing in the events, Royal Air Force teams were on hand as official observers, pointing up the fact that the B-58 is the free world's only operational supersonic bomber. Air Marshal Sir Kenneth Cross, Commander-in-Chief, summed up his observations in this way.
I thought that one of the most remarkable aspects of the competition was the success of the B-58. Whatever advantages they had in equipment, it surely must be unique for the first time in the competition to come out with the best bombing result.
12 January 1961, Edwards Air Force Base, California. 6 new world speed records for payload and no payload flights were established by one SAC B-58 bomber in one flight, carrying a 4,000-pound payload. 5 of these records were held by the Soviet Union. The record-breaking flight was under the supervision of the National Aeronautic Association, which forwards certification data to the Fédération Aéronautique Internationale, Paris, France. NAA observers were at each turning point where official sighting stations were set up to make sure that the bomber, which reached a maximum ground speed of 1,425 miles per hour, did not cut inside the pylons on turns and thus shorten the required course distance. This run was to assault the 2,000-kilometer record, 2 laps around the track with a payload of 2,000 kilograms, about 4,000 pounds. The B-58's 3-man crew were the following: Major Henry J. Dutchendorf, pilot; Captain William L. Polhamus, navigator bombardier; and Captain R.R. Wagoner, defense systems operator. All officers of the 65th Squadron of the 43rd, the Air Force's 1st B-58 bomb wing at Carswell Air Force Base, Fort Worth, Texas. Standing by to monitor the flight path were the crew's commanding general, Major General Nils Oman, commander of the 19th Air Division of the 2nd Air Force, and their commanding officer, Colonel James K. Johnson. Chase planes carrying NAA observers could keep up with the Mach 2 B-58 only for short stretches. Heavy reliance was placed on ground observers and tracking cameras for certification data. Even the tracking radar was pushed to the fullest to keep up. As it crossed the starting line, NAA officials timed it and watched its climb to altitude. Altitude is checked by onboard barographs, NAA officials in observation planes, and tracking cameras. 1,061 miles an hour was the average speed, establishing 3 new world's records for the 2,000-kilometer run, 2 laps around the 1,000-kilo course. The speed on the second lap, 1,200 miles per hour for 1,000 kilometers, established 3 more new world's records. General Thomas S. Power at SAC's headquarters in Omaha, Nebraska said, "The major significance of these B-58 record flights is that they have dramatically proved the capabilities of SAC's first operational supersonic bomber." 14 January 1961, Edwards Air Force Base, California. An Air Force B-58 Hustler today broke 3 of the 6 world speed records set only 2 days earlier by another B-58. Major Harold E. Convair was pilot, and his crew, officers of the 43rd Bomb Wing, were Major Richard H. Weir, navigator bombardier, Captain Harold S. Bialas, defense systems operator. Today's records, like those on January the 12th, were set with the aircraft in an uphill climb. Major Convair's plane crossed the starting line at 40,000 feet and finished at 50,000. The flight required him to make a 185-degree turn over NAA-monitored pylons, maintaining a 60-degree bank angle throughout the turn and pulling more than 2 Gs, twice the force of gravity. From the ground, its turn looked razor-sharp, cutting the pylon close and clean. The least cut inside the crosshair would have aborted the mission. Major Convair's crew closed the 1,000-kilometer course with an average of 1,284 miles per hour, nearly 100 miles an hour faster than the B-58 record set 2 days earlier. Today is now. As scheduled, 2 B-58s left Edwards Air Force Base after their week of record-breaking high-speed runs to return home to Carswell Air Force Base. On the way, they flew simulated missions. Major Richard Weir, navigator bombardier of the Roadrunner, got a shack, a direct hit, on a practice bombing run. Captain Bill Polhamus of the Untouchable turned in a score that was well within aircraft specifications. Not an ordinary day, not an extraordinary day for these B-58s, but a special one certainly for their crews. A homecoming welcome. Today, the story at Carswell Air Force Base is that the first wing of the world's first supersonic bomber is operational, willing, able, ready. This was stated forcefully by General Keith K. Compton, SAC's Deputy Director of Operations, at the close of the 1960 combat competition.
The superb bombing of the B-58 force in this competition definitely proves that the SAC now possesses a positive supersonic bombing competition capability. This competition has proven beyond a doubt that this weapon system is a potent, alert vehicle with a positive, accurate striking power.
Open Road 3 was the program to develop and test a minimum interval takeoff capability for B-58 aircraft under simulated wartime conditions. The program was conducted during the period 14 to 22 January 1963 at the Air Force Flight Test Center, with the aircraft seen arriving here. The program had two objectives. The primary objective was to determine a minimum safe takeoff interval between aircraft. This included an evaluation of such factors as ground turbulence in the wake of preceding aircraft, aircraft jet wash after liftoff, effects of atmospheric conditions, and the effects of AV light on pilot vision, all under both day and nighttime conditions. The secondary objective was to develop a technique for rapid deployment of multiple numbers of aircraft using MITO. This included observance of all checklists and operational requirements, and taxi from a simulated alert posture under wartime scramble conditions. The test program was divided into 7 test series and included taxi tests as well as in-trail takeoffs and alternate guideline takeoffs at both normal training and maximum gross weights. The program was directed by Strategic Air Command Headquarters and was conducted by the 19th Air Division. Participating in the program were 6 B-58 aircraft and their maintenance and flight crews, 3 from the 43rd Bombardment Wing at Carswell Air Force Base, Texas, and 3 from the 305th Wing at Bunker Hill Air Force Base, Indiana. The first day's testing was devoted to establishing taxi procedures. These studies were made during the day and again that night. These tests were used to verify scramble ground check procedures, to determine how to control the space between aircraft without excessive use of brakes and throttle, to determine the proper speed and radius for turning onto the runway, how to accelerate through the military power to afterburner range while rolling, and to determine whether or not airflow, noise patterns, and afterburner glow would affect the following aircraft. The intent was to make interval spacing solely the responsibility of the individual pilots without any outside assistance. This helicopter view shows the degree of uniform spacing distances the pilots were able to achieve and maintain after only a minimum amount of practice. The taxi distance necessary to achieve a desired 15-second takeoff interval was approximately 300 feet. Standard spacing for lights on taxi strips is 200 feet at Air Force Base installations. By maintaining a 1.5 light space between a leading and trailing aircraft, a 300-foot or 15-second separation is automatically achieved. For any interval more or less than this, of course, the distance would be adjusted accordingly. The pilots found that the separation intervals were relatively easy to maintain by anticipating the use of power and brakes. This circumstance can be compared to the reaction necessary to maintain a correct flight attitude during air-to-air refueling. The planned taxi speed was determined from the 15-second desired MITO interval to be approximately 15 miles per hour. Since aircraft instruments do not indicate these low speeds, a car was used in the beginning to pace the aircraft. The pilots found that they were able to gauge these speeds for themselves after very little practice. The first turns onto the runway were made at 20 miles per hour. When the turn was approximately 2/3 completed, the power was advanced to military and then into afterburner for takeoff simulation. At the completion of the first 2 runs covering taxi to takeoff initiation, it was concluded that this procedure caused the aircraft to veer heavily and could possibly create tire problems under maximum weight conditions. Notice here also that the afterburner on the outboard engine failed to light with the others, and the aircraft veered slightly. This was found to be a very minor problem. Only minimum steering correction was needed to bring the aircraft back to normal while completing afterburner light-off. To best achieve uniform transition from taxi to takeoff, the following procedure was developed during these investigations. The technique involves taxiing out at minimum power. As the aircraft is aligned with the runway, power is advanced to military momentarily, and a check is made of the instruments to ensure that all engines are stabilized. The throttle is then rapidly advanced to full AB. The best afterburner lights were obtained using this procedure, and no tire damage was incurred. Results of the initial taxi tests revealed that no major problems existed in this phase of the operation. The second day of testing was the beginning of the actual flight portion of the program. These tests were made with the aircraft working in pairs from a standing start position. The purpose here was to determine a minimum safe interval between 2 aircraft taking off in trail on the same guideline. These helicopter views were taken with a slow-motion camera and do not reflect real-time intervals, which were actually much shorter than they appear in these high-angle scenes. These tests were made at a training gross weight of 150,000 pounds. The objective here was to start with a time interval that was well within anticipated safe limits and reduce that time to study the effects of backwash and turbulence on the trailing aircraft. The unstick time interval between the first pair of aircraft was 30 seconds. Between the second pair, the time interval was reduced to 19 seconds. The unstick interval between the final pair of aircraft was reduced to 16 seconds. No problems of any kind were encountered. The pilots reported that these close interval single-line takeoffs were very much like normal individual takeoffs, with no special turbulence or backwash effects noted, even at liftoff and initial climb-out. After liftoff, the aircraft followed the accepted alternate left and right turn pattern. In all instances, the takeoffs were evaluated as completely safe. Following our single guideline tests, multiple aircraft takeoffs were examined using an alternating aircraft sequence on parallel guidelines. The 2 lines were separated by a distance of 100 feet. As in the initial takeoff tests, the aircraft were worked in pairs, with the time intervals being gradually reduced until a minimum safe time interval was reached. These first 2 sets of takeoffs were also initiated from standing start positions, with the last pair of aircraft using the rolling turn MITO technique. Takeoff weights were still at the training gross weight of 150,000 pounds. The unstick time interval between the first 2 aircraft was 13 seconds. Time between the second and third pairs was the same for each, at 6.5 seconds. Pilots reported that no severe backwash or turbulence was experienced. The worst condition that was encountered was compared to what is customarily experienced in routine rough air takeoffs. This view shows one of the aircraft experiencing a minor wing down condition. At no time was more than 5 degrees of wing down noted. The maximum stick displacement necessary to correct for it was approximately 3/4 of an inch. With the ability of the B-58 to perform these takeoffs now fully established, multiple aircraft takeoffs using the rolling technique were tested. These demonstrations were made under both day and nighttime conditions and included flights with the aircraft at the maximum gross weight of 163,000 pounds. All 6 aircraft participated, and basic interval spacing was now initiated at the beginning of the taxi runs from the ramp area. Significant throughout this entire exercise was the fact that conditions completely simulated those that would be found at any SAC air base. Aircraft support was handled entirely by SAC maintenance crews brought in with the aircraft. Although the Edwards airstrip is much larger, the runway area used in these tests was limited to the typical 200-foot width, 12,000-foot length SAC runway. The guidelines shown here were painted on especially for this exercise, just as they could be at any base where B-58 minimum interval takeoffs are needed. The guidelines can be added with minimum effort in just a few hours' time. The turn pattern is established by following and spot painting the trail of a B-58 taxiing at 15 miles per hour. Painting of the lines can then be accomplished with available line painting equipment. The runway guidelines are 100 feet apart, paralleling the center line, and extend 1,000 feet up the runway after the turn. Unstick intervals for the 6 aircraft maximum gross weight takeoffs averaged 15.4 seconds. No problems of any serious nature were encountered, and all aircraft were in a combat go condition after becoming airborne. Pilots reported that the entire exercise was very routine. The importance of the taxi phase of the operation cannot be overemphasized. The key to achieving the proper time interval is in maintaining proper spacing all through the taxi phase of the minimum interval takeoff. Tire checks were made in all takeoff operations just as in normal single aircraft B-58 takeoffs. These were made approximately 1,000 feet before reaching the head of the runway, and proper taxi intervals were maintained. Abort procedures are similar to those outlined in the handbook. In the event of an emergency, the pilot in the problem aircraft simply calls out the standard, abort, abort, abort. Those aircraft at speeds greater than S1 decision speed are not affected. Aircraft at speeds less than S1 immediately go into accepted stopping procedures straight ahead if they have already initiated takeoff rolls. The MITO nighttime tests included taxi runs and demonstrations of multiple aircraft takeoffs using the established rolling technique. Both maximum training and maximum tactical gross weights were used. The ramp training weight was at 150,000 pounds. The ramp tactical gross weight was 163,000 pounds. Here, aircraft running lights are contrasted with the runway lights as aircraft taxi from left to right. Pilots reported no ill effects in the taxi portion of the nighttime runs. This film shows the engine flame as being white. This is a peculiarity of the film itself. Engine afterburner flame actually appears a soft blue-yellow in color. 2 separate nighttime sorties were made on the final 2 evenings of the program. There were no problems found in pilot reactions to the afterburner flame from the aircraft ahead at any point in the takeoff roll or climb out. Attempts were made to get readings on a light meter from the plane ahead, but there was not enough light to get even a minimum reading. Pilot reports as to the lack of light problem were supported by the flight surgeon from the Air Force Flight Test Center. These night sorties confirmed that minimum interval takeoffs of multiple B-58 aircraft could be done in a routine manner with only a minimum amount of training. The training gross weight night takeoffs were made at an average unstick interval of 11.6 seconds between aircraft. Maximum gross weight nighttime unstick intervals averaged 15.4 seconds and fully demonstrated the satisfactory achievement of all Open Road 3 program objectives. The B-58 long ago demonstrated its ability to stand operational ground alert and to be kept on a ready basis for any eventuality. It is also demonstrated that it can get wheels rolling in 2 minutes and 5 seconds under simulated combat mission conditions. The effectiveness of any weapon system is summed up in its ability to answer the call and deliver its punch at the precise moment it is needed. To protect a long-range missile, you bury it deep in the ground in a hard site. To protect an airplane, you get it airborne. Today, in the event of an attack, the early warning system will provide us with about 15 minutes reaction time. With the now demonstrated ability of the B-58 to scramble in numbers using the ground alert and MITO techniques, we are assured that its chances of getting caught on the ground are greatly reduced. Our demonstrations were made using 6 aircraft, but the MITO ability can be programmed for any number, at any time, at any SAC air base.
The first trainer version of the B-58 was delivered to the Air Force in August of 1960. Its assignment, the training of Air Force pilots in the handling of the Mach 2 B-58. The trainer proved to be a dependable airplane from the beginning of its service. In the first 2 months of its service, TB-58 number 1 qualified 6 pilot instructors and 7 B-58 pilots. The story of how this special airplane came into being begins in August of 1959, when the Air Force assigned Convair the task of developing a total of 4 trainer aircraft. In the interest of overall economy, it had been determined to convert research and development aircraft to the trainer configuration, incorporating such alterations as might be necessary. As a preliminary step, a mock-up was constructed to show just how the conversion airplane would do the job. Incorporated were various changes arrived at through design studies. These included rearrangement of the second station, additions to the control system, as well as changes in instrumentation and cockpit lighting. The new second station occupies the space which formerly housed the electronic equipment for the bombing navigation system. This system, together with the active and passive defense systems, have been removed from the TB-58 as unnecessary for flights devoted exclusively to pilot training. The elimination of these systems brought about a considerable saving in the cost of the trainer. In the new second station, we find the pilot instructor's seat set 40 inches behind the first station and 10 inches off-center. In the bulkhead between the 2 stations, windows have been installed on either side of the ejection rail housing. In October of 1959, Research and Development Airplane number 11 was transferred from the flight test pool to the conversion program. With the acceptance of the elements of redesign required in the trainer B-58 by the Air Force, the actual conversion of a Hustler got underway. With the conversion work complete, Airplane 11 was ready for ground checkout. The schedule called for ground run-ups of newly installed engines, low-speed taxiing to evaluate ground handling characteristics and nose wheel steering, a high-speed taxi test to check the dual control system, brakes and drag chute, and visibility checks from the second station. After satisfactorily completing its ground checkout, Airplane 11, now TB number 1, the first of 4 B-58 trainers, was ready for its first flight.
Roger, 670, are you ready for takeoff?
670, Roger.
You take off on the right side of the active. The wind's 160 degrees at 5 knots, cleared for takeoff.
Roger, advancing power.
On 10 May 1960, B-58 trainer number 1 lifted from the Carswell runway at a takeoff weight, lacking pod, of 97,000 pounds.
B-58.
Other Convair shakedown flights were scheduled for the trainer while carrying a pod.
You call high key.
Oh, Roger, will call.
The crew performed regular test flight functions with emphasis on qualifying systems unique to the trainer, especially the dual control system. The transfer of flight control from station to station was practiced. In actual training, the pilot qualifying for the B-58 will get preliminary general indoctrination while flying in the second station, with the instructor occupying the pilot station. After this, the in-training B-58 pilot will move to the front seat for the major portion of his flight checkouts, a procedure comparable to that employed in earlier aircraft having a tandem seat arrangement. The instructor in the second station will have, of course, an override capability at all times. While provided with these arrangements purely for training purposes, the TB has flying qualities identical to those of the operational B-58. For the prospective B-58 pilot without previous experience in delta wing aircraft, some readjustment may be required in his early acquaintance with the Hustler. But during his carefully supervised program, he will soon discover that the stability inherent in this planned form, the ease of control augmented by its highly automatic equipment, the experience of sustained Mach 2 flight without strain, have given him full confidence in himself and his aircraft. With the imparting of this confidence, the chief goal of the non-tactical configuration of the B-58, today the TB-58 is achieving this goal quickly, economically, and dependably.
Since the beginning of aviation history at Kitty Hawk, preservation of human life has been the airman's chief concern. Many methods have been used, from the early days simple parachute to the complicated high-altitude pressure suit of the 1950s. But in 1962, for the first time in history, the men who fly the supersonic airplanes have the means to save their lives without injury or appreciable discomfort when a disabled aircraft must be abandoned. This is one of the chapters in the story of Escape and Survive. In 1958, the decision was made to design and build an encapsulated seat for the ejection of an airman from the new supersonic Air Force bomber, the B-58 Hustler, manufactured by General Dynamics, Fort Worth. The job of design and development was awarded to Stanley Aviation Corporation of Denver, Colorado. From the beginning, many problems were apparent. After study and research, the control and stabilization of the capsule was accomplished by fins, which extended aft from the capsule, and a stabilization chute. The testing of many chutes in wind tunnel tests and high-speed sled tests resulted in the Hemisflow ribbon parachute. Thus began 3 years of intensive testing and retesting to develop the new capsule. Daisy track tests to develop harness and torso suspension devices. Supersonic sled runs to test ejection characteristics. Initial landing impact tests were accomplished by dropping the capsule to simulate landing rate of descent. Aerial drops from the Stanley T-28, testing flight characteristics. After the general configuration had been determined, the subsystems began to take shape. The Stanley capsule was designed to permit the airman the utmost freedom of mobility, comfort, and utility. It incorporates all the necessary features to assure absolute reliability and completeness of survival functions. During normal flight and mission time, it serves as an adjustable seat. Realizing that most pilots will never use the escape system for its primary purpose of escape and survival, it is unreasonable to encumber the airman with cumbersome pressure suits. By eliminating this, the Stanley capsule exemplifies the concept of shirt sleeve flying. The redundant capabilities of the capsule, opening and closing devices, permits fly down while doors are closed. The flight stick is an integral part of the capsule, and instruments are readily visible through the large plastic window. If the emergency ceases to exist, the doors may be opened and normal flight continued. While testing on the subsystems was being completed, more sled runs were made to test all systems during ejection. And a high-altitude drop from a B-47 to test the main recovery chute. Ground rocket firings were made to test the escape rocket used in the capsule. A special structure was constructed at the Stanley plant to test landing impact. Under controlled conditions, the capsule was dropped on a variety of landing surfaces: dirt, concrete, and water. In early tests, animals were used, and later human subjects were tested. One of the prime requirements of the capsule is the universal survival capabilities. Over 50 pieces of survival equipment, including a 3-day supply of water and a 14-day food supply, are designed to fit into small containers tucked away in the capsule. Flotation tests were conducted under a wide range of climatic conditions from tropic to Arctic, including a survival test on Lake Erie in the dead of winter. The subject lived in the capsule 72 hours. During this time, he was subjected to severe Arctic conditions, sub-zero temperatures with ice forming on the capsule and buffeting of heavy seas. After the test, he was examined by medical personnel and pronounced hale and hearty. The final testing began with a static firing from a supersonic bomber parked on the runway. Next, a series of supersonic ejections were from a sled on Hurricane Mesa carrying animals. The mesa provides a recovery fall of over 2,000 feet at the end of the 2-mile track. Preparation for the tests are exacting. rockets are installed and armed. The warning is given.
20 seconds till firing. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire.
Results showed no disabling injuries occurred during the ejections. After this, an operational capsule ejection was performed from an airplane rolling down the runway at 100 knots. This test emphasized the unique capacity of the capsule to eject and recover from a disabled aircraft during landing and takeoff. In February 1962, the first manned escape test was successfully performed above Edwards Air Force Base. High-speed cameras placed throughout the plane show with dramatic proof the Mach 2 capabilities of the only operational escape capsule in the world today. In high-speed regime, only a capsule can provide safe escape and confidence in the capabilities of survival. This confidence has been developed by an unprecedented number of test ejections with animals and humans. The Stanley capsule has completed all the qualification tests and is now operational. Thus, another important step is completed in air safety, and the practical application is made of escape and survive.
As the first airplane capable of sustained cruising at supersonic speeds, the B-58 presented a unique problem: how to escape safely in case of emergency from aircraft performing long-range, high-altitude military air operations. In solving this problem, several demands had to be met. The most important was the provision of a proper environment for survival during ejection, descent, and landing. In this last category, both ground and water landings had to be reckoned with, as well as a range of climatic conditions varying from tropical to Arctic. Other requirements were that the system should allow full in-flight operational freedom for the crew at all three stations and installation in the tactical aircraft with a minimum of modification. Going beyond these specifications, the Air Force and Convair, working together, hoped to provide a basic design of escape system capable of broader application than ever before envisioned. This meant discarding the design approach involving the detachment of an entire section of the fuselage for escape. It also meant that the ejection system evolved for the B-58 must fit the space envelope requirements for current conventional seats of any or all high-performance aircraft. A starting point was found in the ejection seat of some years ago. In line with the space envelope concept, an interim ejection seat fitting the conventional rails and requiring no change in the canopy or cockpit was developed for the B-58. This system incorporates several major improvements. One is the addition of extremity restraints, which will ensure far better protection against flailing after ejection than the current standard seat. Another is the replacement of the standard catapult by a rocket catapult to provide greater force for safe clearance. While the interim system remains just that, an intermediate step pending development of the fully perfected escape system, this equipment is currently the best available. Meanwhile, under contract from Convair, the Stanley Aviation Corporation of Denver, a small but highly capable concern, was awarded the task and is now designing and developing an escape capsule for the tactical B-58. Despite its present familiarity, that word capsule is still significant, for it embodies the principle of total encapsulation, which is the only possible answer for crew survival at the speeds of modern aircraft. Now, let's turn to an animated representation to see how the escape capsule, as installed in the B-58, will provide this maximum safety for all crew members, as well as accomplish other basic targets of its design. Again, using the conventional rails of the original ejection systems and requiring no major structural changes, the capsule has two configurations, one for the pilot station and another for each of the two crew stations. Their basic principle of operation, however, is the same. For purposes of demonstration, let's concentrate on the pilot station. As an example of operational freedom for the crew, the capsule, having its own pressure, oxygen, and recovery systems, eliminates the need for pressure suits, bailout bottles, and parachutes. Thus, the pilot and other crew members enjoy the same self-sufficiency at high altitudes as at low. This shirt-sleeve flying also contributes greatly to crew efficiency. Now, in slow motion, let's follow the pre-ejection and escape cycle. In case of high-altitude decompression, the pilot seeks immediate protection by closing the capsule. Note how the flight control stick, being an integral part of the capsule, permits control of the plane from inside the capsule. Another important advantage is that even with the capsule closed, he can still communicate with the second and third flight stations. Next, by means of push-button controls on the stick, he can move the center of gravity forward, retard the throttle, and fly down to a habitable altitude. Observe how the large front window allows him a view of his primary flight instruments. Once arrived at lower altitude, he may now raise the capsule door manually and continue flight. In case the airplane must be abandoned, the pilot waits for the crew members in the third and second stations to eject. He then squeezes the release handle for ejection of his own capsule. After the canopy has been jettisoned, the catapult is actuated and the capsule ejects. The rocket reduces the deceleration rate, while the stabilization system prevents tumbling and excessive G's on the occupant. With escape being made at less than 15,000 feet, the recovery system is actuated when the capsule reaches its peak of trajectory. First, the stabilization system is automatically detached as a deceleration bag, whose prime function we'll see later, inflates to aid in deployment of the main recovery chute. Should escape have to be effected above 15,000 feet, an aneroid device puts the recovery system into operation. In either case, outrigger booms are ballistically swedged into an extended position. As will soon appear, their purpose is to aid landing on the ground or at sea. Hanging by two risers from the main recovery chute, the capsule floats down at a rate of 25 feet per second. Its landing attitude is 36 degrees toe down from the vertical, while the deceleration bag is so located as to receive the mass of the impact. On impact, the chute is detached so that the capsule will not be dragged and the crew member can free himself without difficulty. Now let's see what happens in the case of a water landing. When the capsule submerges, bladders, which are actuated by a water sensing device, inflate. Its downward motion quickly arrested, the pressurized capsule returns to the surface. Its 4 flotation outriggers hold it in a fairly stable position. One requirement for the capsule is the capability to withstand 72 hours of high seas. Gear packaged for easy availability within the capsule has been carefully designed and selected to give maximum aid and survival on the water and on land, whether under tropic or Arctic conditions. Whatever the environment, the capsule may serve as a valuable shelter. This completes the escape cycle. Before leaving it, let's go over the key stages in its operation again. First, ejection. Next, the deployment of the stabilization system, followed by that of the main recovery system. Finally, note how the ground landing is made with the capsule in a toe-down position with the deceleration bag making impact tolerable. While at sea, the outrigger bladders do their job of keeping the capsule stable until rescue. To ensure meeting specifications, a thorough program for testing the capsule's components is underway. For instance, here the booms on these same outriggers are having to prove they can hold the locked position over the required 3 days of rough sea conditions. Here, Stanley technicians, using a 510-pound mass to simulate the weight of capsule and man, test drop the deceleration bag to assure satisfactory slowing of the capsule before impact. At the Joint Navy-Air Force Parachute Test Center, El Centro, California, trials of several configurations for the main parachute and the capsule's recovery system were made for selection of the one achieving best performance figures. Similarly, choice of the stabilization chute with its vital role in crew survival during ejection was based on a series of tests for as many as 11 competing configurations. The chute seen under test here happens to be the winner. Other tests, based on the principle of simulating the weight, center of gravity, and aerodynamic properties of the actual capsule, are being conducted at Mesa, Arizona, and Hurricane Mesa, Utah, to ensure that performances measure up to specifications. Today, under the impetus of this many-sided program of design, test, modification, and retest, the escape capsule is approaching finalized form. Present plans call for its installation in tactical aircraft being delivered in late 1960. It will be retrofitted in the field to all B-58s previously delivered to the Air Force. As we look beyond the B-58 and further into the future, the basic concept of the totally encapsulated seat may find broad application to all supersonic aircraft. And so the escape capsule may well have achieved a new Kitty Hawk in the realm of air safety.